Soil is a dynamic, heterogeneous, three-phase porous media. But soil particles are very small. Some of them are too small to be seen with the naked eye. The spaces between those particles also can be either large or small. And since we cannot see and perceive all of those things that are going on in a soil, in an aggregate or a sample, we often use models such as these glass beads. These glass beads are different sizes, from 25 millimeters down to 1 millimeter. We can observe these and note that the spaces between the largest beads, the 25 millimeter beads, are very large, so it has large pores. The spaces between the 10 millimeter beads are smaller. The spaces between the 5 millimeter beads are smaller yet, and the 1 millimeter beads are very small. We're going to take water and pour it into these cylinders. These cylinders each have 100 milliliters of beads in them. So we know a total volume. We're going to take 100 milliliters of water in a graduated cylinder and see how much these cylinders will hold with these different sizes of beads. We're going to weigh those as well. And then we're going to pour the water from the graduated cylinder with the beads back into the one with the water, and we will determine how much water stayed in the beads, as well as how much water was in the pores when the soil was essentially saturated, or in this case, the beads were essentially saturated. So we use the beads as a model to look at things that we can't see with our naked eye. So what kind of data do we have? Well, we know that the container volume, those graduated cylinders, have a volume of 100 cubic centimeters, 100 milliliters. Those are the same thing. I started with 100 milliliters of water, and I poured that water into the graduated cylinder, and when I was done, this graduated cylinder still had 58 milliliters of water in it. So what does that tell me? Well, if I do some quick subtraction here, 100 milliliters minus 58 milliliters, what I find is that 42 milliliters of water filled the pores in the 25 millimeter beads. So when I'm looking at my table, it says the water in the beads in milliliters. Well, the water in the beads in the 25 millimeter case is 42 mils. We can do the same process as we work our way across. And we say, well, I've got 100 milliliters minus 44 milliliters. That was supposed to be minus. There we go. We end up with 56 milliliters of water in the 10 milliliter beads. 10 millimeter beads. 100 milliliters minus 52 milliliters. That's 48 milliliters in the 5 millimeter beads. And then we get to the 1 millimeter beads, and we end up with 42 milliliters of water in the 1 millimeter beads. The table up here, we'll reproduce it. We have we have 25 millimeter beads. We have 10 millimeter beads. We have 5 millimeter beads and 1 millimeter beads. we now know the water in the beads in milliliters was 42 in this case, 56, 48, and 42. The next calculation that it asks us to do or to recognize is the pore volume. Since we're using a model here in cubic centimeters, we already know previously that 1 cubic centimeter is equivalent to 1 milliliter. An assumption we're making at this point is that all the pores in the soil, in these marbles, graduated cylinders with marbles, all those pores were filled with water. That we'll see later that assumption is probably not valid, but it's a working assumption that we have now. So if that's the case, then the pore volume was the amount of volume of that cylinder that was filled with water. So in this case, these numbers are the same. 42 cubic centimeters, 56 cubic centimeters, 48 cubic centimeters, and 42 cubic centimeters as the pore volume. Now, as we continue this process, we've got another calculation to work with, and that's asking us for our porosity. It gives us the definition formula of porosity, which is the volume of the pores divided by the total volume. At this point, let's take a quick look at or review of our cube that shows us the connections between volume, mass, and density. Right now, the only data we have is related to volume. So we know that water occupies volume, air occupies volume, and solids occupy volume. We know that air and water exist in the pores. And then we know that the total volume is the sum of the pores and the solids. At this point, we have to stop and think, okay, what is porosity? Well, it's the volume of these pores, the relative volume of the pores, to the total volume of the container. The volume of our container is 100 cubic centimeters. So our total volume here is 100 cubic centimeters. And the volume of the pores in each case, as we're using the water that filled the pores as an indicator of that, is here. So we're going to find, in this example, for the first one, for 25 millimeter beads, it's the 42 milliliters. Actually, let's put those in cubic centimeters. 42 cubic centimeters, and we're going to divide that by 100 cubic centimeters. And so for the first case, we get 0.42. And the units for porosity, as you'll see up here, are cubic centimeters per cubic centimeter. We replicate the process across. And when we do, go ahead and put our bead sizes up here again. Then our porosity in cubic centimeters per cubic centimeter was 0.42.